My name is Katie Bear. I'm a research ecologist with the Forest Service based out of Anchorage, Alaska. And today I'm going to be talking a little bit about our urban forest inventory and analysis program and some of the results from the two first Western US cities that have had their inventories completed in the last few years. So I will try to zip through this because there's a lot to cover. Urban forests have been getting a lot more attention lately. I think people are beginning to really recognize all of the services that urban forests provide, including providing sort of ecological services in terms of habitat for wildlife and other plants, providing benefits as far as removing air and water pollution, and also, public health benefits, mental health, physical health related to the removal of pollution, and also sort of improving social cohesion in the recipient communities. So this increased awareness of the benefits associated with urban forests led to a directive in the 2014 Farm Bill for the U.S. Forest Service's Forest Inventory and Analysis, or FIA, program to expand the scope of its inventory of the nation's forest resources into the urban forests of some of the nation's most populous cities. So that's when Urban FIA was born, or UFIA. We love our acronyms, so I'll be referring to it as UFIA throughout the rest of the talk. And in order to carry out this inventory of urban forests throughout the nation, the UFIA program partnered with the Forest Service's iTree program to quantify the urban forest resources in the most populous cities, and then also to take that information regarding forest resources and quantify what the services are that are being provided by these urban resources, and try and get an idea of the monetary value associated with those resources. It's a very complex, very, well, it's hundreds of pages of protocol, so I'm not going to go too much into the weeds in terms of everything that's done as part of this protocol. But the gist of it is that it provides a standardized sampling of urban forest resources, primarily focused on trees, although we do look at understory in terms of shrubs and invasive species and a few other attributes. But the idea is to gauge the condition, the health of the urban forest, and then to monitor through time, get an idea of how the urban forest is growing, how mortality is changing. So it's not just a single snapshot, but it is a moving picture through time of what's going on with the urban forest in the cities that are being monitored. This is the only comprehensive forest inventory spanning the nation that covers both private and public lands. So it gives us a really comprehensive snapshot of what's happening in these urban forests, and a comparable snapshot, so we can compare between cities what's going on with urban forests. And we try very, very hard to ensure that we're partnering with local agencies, because these are the agencies that have the power to use these data to affect change, to ensure that these data are being used for effective management in these urban systems. So this is just a map showing some of the cities where inventory has been completed in the past or is slated for completion in the future. And today I'm just going to be talking about the two Western US cities that have been completed to date. San Diego, whose first inventory was completed in 2017, and Portland, Oregon, whose inventory was completed in 2018. This just shows kind of a map of the sampling area of these two cities. I do want to draw your attention to the fact that the scale bars are quite different here. San Diego is a much larger city than Portland, but regardless of the actual area of the city or the area that's sampled, across the board, UFIA tries to install roughly 200 sampling plots throughout the study area. So the goal is 200, depending upon whether we can get access to these plots, because it does involve a lot of work in terms of getting landowner permission to access the plots. We end up usually with somewhere in the vicinity of 200, sometimes a little bit lower. So in San Diego, 185 plots were surveyed in 2017. And this is on a 5-year remeasurement cycle. So 1/5 of those plots will be remeasured every year until in 2022, we'll have a full remeasurement cycle in that city. So we'll have the ability to compare how things are changing through time. In Portland, 189 plots were surveyed in 2018, and this is on a 10-year remeasurement cycle. So in 2028, we'll have a full remeasurement that we can compare to the original measures. There are a lot of data. I want to start out by saying this is a really sort of broad, shallow overview of the data that are available, and I'll show you where these data are available if you want to dig a little deeper into them. But I thought maybe we could just kind of go over some of the highlights from these inventories, and then I'd be happy to answer questions later on if there are additional questions. But the first thing I wanted to start out looking at is just land cover in a really broad sense. FIA on each plot will describe the land cover and the land use of the plot. And because this is a comparable or a standardized protocol, we can compare among cities and say, for example, that impervious cover tends to be much higher than tree cover in San Diego as compared to much higher tree cover with respect or in relation to impervious cover in Portland. So much more tree cover in Portland than in San Diego. We can make these kind of comparisons. It's not necessarily the most accurate way to describe something like tree cover in these cities because an aerial survey gives you a much better idea than a plot-based survey, but this allows us at least to compare between cities what's going on with these urban forests. We also can talk a little bit about tree composition. The estimate for San Diego is about 1.9 million trees that are greater than or equal to 5 inches in diameter. And the most common trees that are really large diameter, these are going to be the ones that are super visible in the urban forest, include a lot of palm trees. So Washington fan palm, queen palm, date palm, and things like melaleuca and Canary Island pine. But an interesting pattern in San Diego is that none of these 5 species actually show up among the most commonly counted trees by stems. Those are all much smaller diameter trees. So this gives us an idea that we have a lot of small young trees in San Diego and not a whole lot of really large diameter trees. In contrast, in Portland, we have about 2.7 or an estimated 2.7 million trees greater than or equal to 5 inches in diameter. And the most common trees there are things like bigleaf maple and Douglas fir, red alder, Oregon ash, western red cedar. And both bigleaf maple and Douglas fir were among the most commonly recorded trees. So it's much more common to have large diameter trees in Portland than it is in San Diego. We also look with the UFIA program, as I mentioned, at some of the ecosystem services provided by these urban forests. And one of the big ecosystem services is carbon storage and sequestration. So storage refers to the amount of carbon actually stored in the bodies of these trees. Sequestration is an annual measure, so how much more is sort of being added to the tally on an annual basis. In San Diego, we were looking at about 289,000 tons of carbon storage. In Portland, more like 1.6 million, so quite a bit more. On an annual basis, trees in San Diego are sequestering roughly 35,000 tons per year. In Portland, more like 50,000. So again, more, but slightly more comparable than when we look at carbon storage as a total. There are also a host of other ecosystem services that are reported on in the reports that we put out about these cities, or we will be putting out. We're in the process of getting them published now. One of the things I sort of talked about a bit at the top of the talk was the fact that urban forests remove airborne pollution in the cities, about 450 tons on an annual basis in each of these 2 cities. They, as a result of reducing this pollution, also reduce the incidence of acute respiratory symptoms by hundreds of cases per year. So that's another benefit conferred by these urban forests. Much higher reduced runoff if we look at Portland compared to San Diego, but that could also be because Portland is a much rainier city than San Diego. Trees, as a result of sort of shading or aiding in heat retention, can reduce the amount of energy that's used by buildings to either heat the building or cool the building. So we can kind of quantify that. We're reducing energy use in Portland by about 250 gigajoules as a result of this urban forest versus 67,000 gigajoules in San Diego. And kind of related to that, we've got a reduction in carbon emissions in both cities that's reported on in these reports. So we can take all of these ecosystem services together and get an idea of what is this forest worth? If we had to put a number value to it, if we had to quantify that monetarily, what would that be? And that's kind of our compensatory value. In San Diego, compensatory value of the urban forest is estimated at $4.7 billion and $5.8 billion in Portland. So these are really important resources, and we're just kind of scratching the surface with these services that I've reported on. There's much, much more in our data set. Keeping all this in mind and the importance of these forests, we also try to describe what are the major threats to forest sustainability in each city. I'm not going to dig too much into the pests and pathogens. I've kind of outlined them here, but I'm not going to talk too much about them. But we do describe major pest and pathogen threats to these urban forests. In both cities, changes in the climate. So in California, we're talking mostly about drought and fires at the wildland-urban interface. In Portland, things like extreme weather events. So the extreme heat wave that happened last summer, or ice storms that are becoming more frequent, can really threaten the urban forest. And then in both cities, population growth is a concern in terms of sustaining those forests and the benefits that they confer. So it is a session about forest management. How does this play into forest management? There are many, many ways that these data can be used to support sustainable forest management. These are just some of those ways. They can help to identify priority areas for management of dead or damaged trees. We know where these trees are. We've done the survey. They can also identify areas that would benefit the most from future planting efforts, including areas with higher levels of environmental injustice. We identify, as I showed, areas with greater impervious cover, which can usually indicate heat islands or areas that would benefit from additional trees. And then we can also look at which species might be best for future planting. So species that would maximize carbon sequestration or leaf area, or might be most resistant to the threats to urban forests that I talked about before. We can also identify and hopefully mitigate common infrastructure issues from interactions with trees throughout the city. So my time is running short. I'm going to zip through the rest of this. These data are available in several different formats. The first being sort of our raw data that are available from the Urban FIA Data Mart, which is linked here. I'm happy to share the link with anybody that's interested. And also through this really fabulous tool that I wish we had time to go over called My City's Trees, which allows you to create data summaries and data reports that you can how would I say this? You can summarize the data in a lot of different ways using a lot of different sort of topics. So it's a fabulous tool, really great for visualization. And I would really recommend checking this one out. So with that, I'm a very small cog in a very large machine with this project. I was responsible for writing the report for San Diego. My co-author wrote the report for Portland, but there are so many people involved in this, including our local partners. So these are just some of the folks involved on this thank you slide. Many, many more were involved. And I'd like to thank everybody that's helped make this a reality. And with that, if there's time, I'd be happy to take questions.
Before I jump in, I just want to give a quick shout out to my colleagues on this work, Karen Jones, Amanda Schoonmaker, Jill Harvey, and Danny Dagenhart. So for those of you who don't know, seismic lines are narrow linear clearings cut through forests in order to provide access for oil and gas exploration equipment. They're generally anywhere from 1 to 10 meters wide, and it kind of depends on the year that they were cleared, with newer lines being narrower as seismic technology advances. And although they are intended to be a temporary disturbance, tree recovery is found to be actually very slow and inconsistent on these seismic lines, and it's making them a persistent feature on the landscape even decades after they've been cleared. And the photo on the right shows that extensive footprint of seismic lines across Alberta. So what factors are impacting this poor natural recovery of seismic lines? There's a lot of different things that kind of interact, including terrain wetness, soil compaction from the heavy equipment used during the line clearing. There's competition with the disturbance tolerant species, and light availability is often limited by shadows from surrounding tall trees, and repeated use of the seismic lines by off-highway vehicles is another factor that is hindering natural recovery. And so this landscape fragmentation that's associated with seismic lines that aren't recovering has impacts on wildlife habitat use as well as predator-prey dynamics. And of particular concern is the fact that seismic lines have been found to facilitate the predation of woodland caribou, which are a species at risk in Canada. So these findings, in conjunction with the declining caribou populations, have incited calls for seismic line restoration. And these restoration initiatives generally involve things like site preparation, mounding or ripping, tree planting, and sometimes the use of woody materials to create microsites and obstruct access. But due to the narrow linear shape of seismic lines, as well as the remote locations, these linear restoration programs can be extremely costly and can range from $8,000 to $17,000 per kilometer, depending on the treatment type. And then even after restoration, these lines still remain kind of out of sync with the surrounding landscape for decades, potentially until a landscape scale disturbance can reset the system. So our question is kind of, what about forest harvesting? Because many seismic lines overlap with historical or near-term approved future timber harvest areas. And similar to fires, timber harvesting around seismic lines might serve as a landscape level reset and create more favorable conditions for regeneration by removing that adjacent forest influence, as well as that seismic line would benefit from the site prep and the tree planting of that cut block. So although somewhat counterintuitive, there might be an opportunity here to utilize forest harvesting as a strategy to facilitate some seismic line restoration. However, the effect of the strategy hasn't been studied. So our objective was to compare woody species development, tree growth rates, and projected future timber volumes on seismic lines in cut blocks with the adjacent offline cut block forest to determine whether or not the seismic line's footprint is erased within the reforested cut block. So our study area is in northwestern Alberta. It's a boreal mixedwood forest. It's lots of aspen, birch, pine, and some white spruce in the understory. Seismic lines in this area were cleared in the 1980s, and they're all about 5 meters wide. And then within the cut blocks, they were harvested in 2004 and 2005 and planted with lodgepole pine. So making those forests in the study about 15 years old. And we looked at 4 different cut blocks and 8 seismic line transects, each paired with an offline transect 25 meters away from the seismic line. And seismic lines were identified using ABMI's Human Footprint Inventory dataset. So then data were collected within 12 circular plots along each seismic line, as well as the offline transect. And we measured heights and diameters of different tree species, as well as counts and heights of saplings and shrub species. If you're interested in seismic line sampling methodology, we also published a comparison study between 2 methods in Restoration Ecology. And while we were out there, we also collected some tree discs or cookies every 50 centimeters up a small sample of trees to generate some height versus age growth curves. And for larger trees, we just collected a core at the base. Okay, I'll just jump into some results. And so we've basically found no difference in total tree, total sapling, or total shrub density between the seismic line and off the line in the cut block. However, there were some species level differences, and particularly with alder. So this photo shows a boots on the ground view of a seismic line within a cut block, as well as off the seismic line. And you'll notice that on that seismic line, there's a lot more alder. And it's kind of hard to see, but like there are pine and aspen in there as well. But it was a lot of alder. We could often find where that seismic line was in the cut block just by looking for the really dense alder. And then looking at a couple of soil parameters, We found no difference in the soil bulk density within the top 15 centimeters, but there was a significantly shallower LFH organic layer on the seismic line compared to off the line. So now looking at the trees, we found no significant differences in tree species counts on and off the seismic lines, and all the transects exceeded 90% stocking. However, the aspen counts were generally lower on the seismic line, and the aspen in these cut blocks is naturally regenerating. And so we think that could be related to pre-existing root structures or potential vegetation competition on the seismic lines, maybe with the alder. And then looking at the heights, there we found that birch was slightly taller on the seismic lines by about 70 centimeters on average, and pine was slightly shorter on the seismic lines by about 40 centimeters on average. And now looking at the kind of understory, our saplings and shrubs, we found with regards to the saplings, there was no difference in the species counts, but white spruce was nearly twice as abundant on seismic lines compared to offline. And these are, again, naturally regenerating white spruce. It was just the pine that was planted here. And then our stats confirmed what we were seeing with the higher alder counts on the seismic lines compared to offline. And the alder was also significantly taller on the seismic line by about 50 centimeters. And that lower LFH depth that we saw on the seismic line could be suggesting that there's less soil nutrition on the line. So that ability of alder to fix nitrogen is giving the species an advantage and likely contributing to its increased presence on the seismic line. And then we also found that there was a strong positive correlation between alder and the little white spruce seedlings on the seismic line. And those white spruce seedlings are shade tolerant, and so they're likely benefiting from the reduced competition from other shade tolerant species under that dense canopy of alder. And now these are our height versus age growth curves for the first 15 years of tree growth on and off the seismic line. And so we found that aspen was growing about 7 centimeters per year slower on the seismic line compared to offline. And pine was growing about 2 centimeters per year slower on the seismic line. So similar growth rates, but slight differences. And these differences could be associated with the competitive effects with alder on that seismic line or with that shallower organic layer that we found, or there could be other inherent soil parameters or nutrient availability differences that weren't analyzed in the study, but could be contributing to that differentiation in height growth over time. And then lastly, we entered our data into a gypsy model, which is used by forestry companies in Alberta to model future timber predictions. And we looked at timber volume up until 150 years. And so that we looked at each site individually here, comparing on the line to off the line. The seismic line is shown with a dashed line there, and then the rest of the cut block is a solid line. And the yellow lines are deciduous, the green is coniferous, and then that black line is just total. So as you can see, there's some site level variability, but in general, the timber volumes are quite similar on and off the lines, especially the conifers in green. Site 8 looks a little wonky. It had a lot of birch on the seismic line, but generally not huge differences looking 150 years into the future. So based on our findings from data in these 4 upland mixed wood cut blocks, the trees and shrubs on the seismic lines, they are regenerating similarly compared to the adjacent cut block forest, approximately 15 years post-planting. So taken together, these results indicate that despite some species level differences, the seismic line footprint is being effectively erased from the landscape, and it's being synchronized back in with the surrounding cut block forest. So while costly linear restoration programs are being championed and funded by government and oil and gas companies, forestry companies are actually pretty well positioned to facilitate and conduct more of a polygonal restoration work on landscape level scales. And this would also be more cost effective to incorporate these lines as part of landscape level harvest and reforestation, rather than treating each seismic line individually. So in conclusion, the application of these forest management practices in targeting areas of really high seismic line density or incorporating nearby seismic lines into cut blocks, it should be considered as a tool in planning linear restoration programs. And I'll just talk really quickly about a couple other projects we're doing related to seismic lines. We're looking at using satellite imagery to assess forest recovery on seismic lines. We're developing some growth models for trees on naturally regenerating seismic lines. And then we're also evaluating the use of a mobile terrestrial LiDAR technology to conduct vegetation surveys on seismic lines. And yeah, I'd just like to acknowledge these folks for their help in the field and our industry partners. And thanks very much for listening. And I might have time for a question or hold them until the end.
Our next talk is going to be by David Phillips. He's with the Forest Dynamics Lab at the University of Alabama, and he's going to be talking about stand structure and canopy disturbance in relation to spatial patterns in a fire-maintained pinus palustrous woodland. So take it away.
Hello and good afternoon, everyone. This is research that I completed as part of my master's degree at the University of Alabama. This research can be found in full under an article of the same name in Applied Vegetation Science if you want to check it out later. I'll first discuss forest structure and the increasing focus of forest management on enhancing structural complexity. Then we'll cover some general information on longleaf pine ecosystems. Following that, I'll go through the standard goals, methods, results discussion, and we'll conclude with a little bit of management implications. Forest structure includes tree distributions in size and age groups, vertical distributions, horizontal distributions, deadwood, and the spatial arrangement of each of these components. There's been an increased interest in managing for structural complexity, as it's hypothesized that greater structural complexity will increase resilience to future climate change effects. But despite this increased interest, spatially explicit data are often ignored in favor of more easily collected stand-wide averages, which unfortunately, when silvicultural treatments are applied uniformly based off of these stand-wide averages, it fails to recognize the spatial dimensions of structure, and it can produce homogeneous stand structures that lack complexity and consequently have lower adaptation potential than more heterogeneous stands. So in composition ecosystems where compositional diversity is low, it's critical to incorporate this spatially explicit data so that you can enhance structural complexity and therefore enhance the resilience of the ecosystem as well. One such example of an ecosystem with inherently low canopy tree species diversity is longleaf pine ecosystems. Although these ecosystems have monospecific canopies, the ground flora is especially rich. These ecosystems have been considered among the most endangered in the US. They once covered an estimated 37 million hectares, but were reduced in area to 1 million hectares. And remnant stands of longleaf pine that lack structural complexity are at an increased risk of transitioning to alternative states, but intentionally enhancing the structural complexity could increase the resilience and adaptation potential of these ecosystems. And the importance of spatial patterns in longleaf pine ecosystems has been recognized, but it can be difficult to translate the observed spatial patterns and relationships to timber marking guidelines. The overarching goal of our study was to quantify spatial patterns of stand structure and composition in a fire-maintained longleaf pine woodland to provide some initial spatially explicit data that can be used ultimately to inform silvicultural systems. Specifically, we wanted to quantify intra-stand distribution of trees by species, diameter, and canopy disturbance, document local patterns of individuals, clumps, and openings using the ICO approach, which quantifies stand level spatial structure in terms of individual trees, patches of trees, and treeless patches. And lastly, to examine spatial relationships between longleaf pine saplings and longleaf pine and pyrophytic oak trees. This study was conducted in the Okmulgee Ranger District of the Talladega National Forest in Alabama. We subjectively established a 1 hectare permanent inventory site and a longleaf pine stand that exhibited desired species composition and structural conditions. The stand was multi-aged and under a 2 to 4 year prescribed fire rotation. The site was subdivided into 100 quadrats, each 10 meter by 10 meter. We documented species, diameter, breast height, and crown class for all trees. In addition, we georeferenced all trees and longleaf pine saplings. To quantify the age structure and reconstruct canopy disturbance history, we extracted tree core samples from all trees using an increment borer. We then used radial growth patterns observed on the tree core samples to reconstruct canopy disturbance events. We used point pattern analysis to quantify horizontal patterns of trees and canopy disturbance, specifically the pair correlation function G of R, to test for significant clustering or dispersion at 1 meter intervals from 1 to 25 meters. Observed spatial patterns of tree attributes were compared to simulated estimates of heterogeneous Poisson null models. And lastly, we used the ICO method to quantify individual trees and characterize the size and number of clumps and openings within the stand. Trees being those categorized as individuals where their crown does not touch the crown of a neighbor, or clumps if their crown touches that of at least one neighboring tree. And then openings were delineated using Euclidean distance from trees. Clump compactness was calculated using the Polsby-Popper test, ranging from 0 to 1, with 1 being a perfect circle. Moving on to the results and discussion. There was spatial clustering by taxa. There were patches of hardwood species and loblolly pine that occurred within the longleaf pine matrix. Trees in small size classes were spatially clustered. We suspected this was because smaller trees had less time to differentiate through intraspecific competition within regeneration patches. But conversely, there was no significant spatial clustering or dispersion for larger tree size classes. On the left, there's a graphic showing the univariate pair correlation function G of R for detected release events. So the shaded areas represent the upper and lower confidence envelope of 95% for those simulated estimates. The red line represents our observed values within the stand. Values above the shaded area indicate significant clustering, and values below indicate significant dispersion. The release events during disturbance period in which the stand was entered for timber stand improvement, for example, were generally randomly distributed, which could indicate that during these injuries, the stand was uniformly treated, which goes back to the thought of those stand-wide metrics being uniformly applied can create homogeneous conditions within the stand. On the right is the bivariate pair correlation function for longleaf pine saplings in relation to longleaf pine and oak trees. Again, values above the shaded area indicate significant attraction in this case. So on the Pinus palustris saplings and Quercus trees, there's an interval from roughly 3 to 7 where there is a significant attraction of Pinus palustris saplings to the Quercus trees. And on the flip side of that, you have an area below the 17 meter mark where they are significantly repulsed from Quercus trees. Interestingly, there is no significant spatial relationship between the longleaf pine saplings and trees. This could be caused by homogeneous treatments that obscured relationships that would otherwise have been evident. With regards to oak, the longleaf pine saplings were clustered around them at distances from 3 to 9, but repulsed at 17 meters. Recent work has highlighted the importance of fire facilitating oak in longleaf pine ecosystems. Loudermilk et al. 2016 found that turkey oak facilitated survival of longleaf pine on xeric sites. And Johnson et al. 2021 found that longleaf pine saplings were more likely to occur near turkey oak than near longleaf pine stems. So to facilitate longleaf pine regeneration, we think managers should incorporate some retention of fire facilitating oaks in pine woodlands. Shown here are representations of the fixed and variable radius ICO methods. Again, that's the individuals, clumps, and openings. The traditional ICO method uses a fixed radius based on the canopy radius of a mature tree within the system. In this case, an inter-tree distance of 6 meters was selected based on a calculated crown radius of 3 meters for canopy trees. This can be modified, though, to use a variable radius interval based on the radius of individual trees rather than a stand-wide average. Here is the percent distribution of trees within clump sizes at specified inter-tree distances, inter-tree distance being the distance from stem to stem. The variable column represents a variable inter-tree distance based on the modeled individual crown tree radius. Because the estimated average crown radius for canopy trees was 3 meters, we used an inter-tree distance of 6 meters to quantify the percent distribution of individuals and clumps with which to compare our variable tree radius. Using that 6 meter inter-tree distance, individual stems comprise 10% of total trees, but there was 10% clump size contained 50% of the trees within the site. The variable radius modification yielded similar results to this. It lies somewhere between the realm of the 5 to 6 inter-tree distance. Using that variable radius ICO method, the median clump size was roughly 90 square meters with the mean clump size of 125 square meters. And the Polsby-Popper value was 0.57, again, with a circle being a 1. We found that about 50% of the reference site was in an opening, so not directly underneath the canopy. And about 10% of the site consisted of open areas that were at least 2 crown radii away from canopy trees. In stands that don't have a lot of crown diameter variability, the differences in clump identification may not be meaningfully different between the fixed and variable radius approaches, but these discrepancies may become more pronounced in stands that have a greater range of crown diameters. Although the variable radius ICO approach may be more ecologically meaningful, differences may be negligible. And importantly, timber marking guidelines should be based on the fixed radius ICO approach, as it would be easier to allow timber markers to focus on a single tree distance, regardless of the size. And for our implications, to increase forest ecosystem resilience and promote adaptation potential, especially in relatively monospecific stands, managers may wish to increase structural complexity. Analyzing spatial patterns of structure in reference stands allows us to elicit spatial relationships and optimize our efforts to increase the structural complexity. For example, based on the spatial patterns observed in our reference site, a structural target may be to have about 10% of trees exist as individuals, and about half of trees exist in large clumps of more than 10 stems. Further, replicating the irregularity of clumps and openings may also enhance spatial heterogeneity. We caution that our results are from a single 1 hectare study site and that quantitative spatial data are required from additional longleaf pine woodlands to get a fuller picture before we develop widespread implementation of these data into silvicultural systems. But we hope that the data presented here will be a catalyst for others to quantify those spatial patterns so that we can ultimately develop silvicultural guidelines and promote resilience in forest ecosystems. Thank you for your time and attention. I'll take a question if there's time for one.
So I'm Joe Chiang from Alabama too. So just the previous speaker, Dave, talked about the spatial heterogeneity. So it saved me a lot of energy to explain some of my stuff. So I tried to check about the tree size in the forest community at a different spatial scale, especially this kind of small scale. So one thing is you will ask about the tree size. Tree, definitely you have different size, how big tree, how small tree if in the natural forest. The thing is that I try to see what's the pattern across the kind of different scale. Were they all similar or just quite different, So this is kind of my interest and motivation to do this kind of research. So one thing is with the tree size, we talk about the canopy, that size, its volume and its diameter. So this is kind of because the canopy related with DBH. We talk about canopy because canopy is important for photosynthesis, and also canopy layer is also important for biodiversity. Lots of birds, or they make a nest at the tree canopy.
Jean-Juan, I'm just going to interrupt you. Are you still on the first slide, or?
Yeah.
Okay.
Yeah.
Just to make sure that you're not having any more. Sorry about that. Go ahead.
Yeah. So I was talking about explain these things. So the objective, like I said, I try to see in a small piece of forest area, we try to see whether the species richness, different species were in. If you the forest with different species, tree species, it will increase the total canopy volume or not. Second is when whether the kind of tree canopy, whether they follow different pattern or the similar pattern, or like such as power law, based on our previous research or previous hypothesis from other people, and also whether the distribution of the canopy volume, of a different tree follow the same pattern or not. So that's kind of a canopy pattern. And also we try to know whether the distribution of canopy projection area, like the canopy projection area, no matter how deep the canopy, but when they project on the ground, maybe they share similar kind of information. So it's related with sunlight interception, all these things. So all these try to see first need a lot of field work, so we can only test in the small and the forest community. So the community is in Alabama, is in a state park, Untitled State Park. We choose state park because there's less human disturbance over there, such as harvesting over there. So it's purely natural disturbance. So the plot size is like a 1 hectare, 100 meter by 100 meter. That's is a small size, but it takes a lot of efforts, because we need to check everything in the plots, like the tree size, the tree name, and its tree canopy diameter and height, tree height. So, and also we record on the tree's location, like X, Y, their access, their georeference. And also we choose like a 1 hectare, 100 meter by 100 meter, because we have an intention to check whether they kind of can be, it can be divided into different spatial scale, like 1 meter by 1 meter, so you have 100, and 2 meter by 2 meter, 5 meter by 5 meter, all the way to 50 meter by 50 meter. So you have 4 kind of application. And we try to see across the kind of gradients of spatial scale at a small area, whether the kind of scaling law will be the same or not. That's a kind of a purpose to see. So here are some main results. So here is a kind of a spatial scale, 10 meter by 10 meter, 20 meter by 20 meter, 30 meter by 30 meter. And here is the accumulated volume, the tree canopy volume. So tree we consider as a cylinder, as long as you have the diameter of the canopy and the tree height, so you can estimate the volume. So we use the accumulated volume. So we see at each different scales, so we can estimate the kind of. Then we'll see at somewhere all the kind of their relationship are not statistically significant. So no matter 10 meter by 10 meter, to 20 meter by 20 meter, and 30 meter by 30 meter, and others, they're not significant. So this means the relationship between the tree species number and the accumulated tree canopy, they're randomly, they're not like some other we expected, with the more tree diversity, because you have different trees, some with bigger tree canopy, some with small tree canopy that can living under them or between them. But actually, we didn't see this kind of phenomena in this forest here. The second is related with the tree canopy volume. We can find in all different tree canopy volume at a different scale, at different site. They follow the power law, the kind of scaling. Look at the kind of relationship, all significant. But the only thing is the power scaling exponent, they are different. Originally, we consider them, they probably will be concentrated or close, but actually they're not quite close. They're quite different. And also, the kind of power scaling can be used as a polynomial kind of relationship. But all these their parameters are quite different. So this is a kind of things we find. The pattern, yeah, there's a pattern over there. You can use the power law, but the scaling exponent, they are quite different. They're not even concentrated to one fixed number, just a variance. And also, like I see the Taylor's power law, we also checked in. So it's the same things. Each of them, there's a very good correlationship at the different scales, but all the exponents were quite different. So basically, if we across the kind of 1 hectare areas from 1 meter to 50 meter, the kind of scales, you'll see the exponent, they change like in this kind of ways. Somewhere increase dramatically, and somewhere become flat, and at the 40 meter by 40 meter, the kind of scale, it began to decrease. So this is kind of the kind of pattern for the exponents. So exponents means that they are not consistent. Power law, their exponents are not consistent. And also we check different tree species, so like mainly they are oaks, like a white oak and hickories, and so all these they also follow very good power law, the kind of relationship with the canopy volume. But you will see for different tree species, their exponent were quite different. Like a white oak, 0.16 in here. For hickory picnic, hickory is 6.6. So that's quite a deviated this kind of exponent. It's scaling exponent. And then we also check the canopy diameter, the kind of, and related with the projection area. So we see it's the same things for them, like the power law, the frequency power law, and the Taylor's power law. All these kind of exist significant at the different scales, but their exponent, some are very close, some are quite different. For example, 0.25 to 0.24 is 10 meters by 10 meters, 20 meters by 20 meters. So then at 30 meters by 30 meters, change dramatically. So here is Taylor's power law. It's the same thing, 3.3 and then 3.7. The fluctuations. So all these tell us, and also with the allometric relationship between the canopy diameter and the canopy volume. So this is with the 2 dimension, another tree canopy is 3 dimension, but there's the scaling exponent are close to 3.0, like this one is 2.67, this 2.99. So this is kind of pretty close. This is 2.98, pretty close. So this is kind of related with the original the metabolic theory, ecological metabolic theory, that they predicted about 3.0 because of the 2 dimension with 3 dimension. but it's varied with the location and the scales. Some are very close, some are a little bit far away. So this is the kind of basically the kind of main results. So we already find it's a surprise, we find that tree diversity actually did not increase the accumulated canopy volume at a different scale. That's quite different than we expected. Like expected with the tree diversity, you have a different tree shape or different age. So then it should be like with a more higher packing utilization, but actually it's not. And then the second is all the kind of tree canopy or diameter, their distribution, they follow power law. But the scaling exponent were quite different across different scale, especially even under the kind of 100 meter by 100 meter, the kind of small area, they're quite deviated. So that is give us some experience whether we can use one like allometric scaling relationship to apply it for different scale. It's maybe it's invalid for them. And also the allometric scaling relationship, it should be around 3.0 or 1.5, but actually some site at some scale they're close, but at the other area they're not even close. They deviate from either 3 or either 1.5. So that is make the scenes quite different. So that we consider the possible relation, the possible causes. It's related with a natural disturbance or like a windbreak or some disease. All these things can affect the tree structure, canopy structure, other things. Because we measure another 1 time. We do not measure like every year or something. So that's the kind of some results we have, and also we conclude, that the conclusion there's no significant relationship between the tree species richness and the accumulated tree canopy at a different scale. So that's one thing. The second is the power law. We found the power law, but they are the exponents were quite varied. It depends on the spatial scale and the site, and also for different tree species, they're not consistent. So that's the kind of maybe provided the challenge to current the kind of ecological theory, especially the metabolic theory about whether we can use one number, one exponent, like a 3/4, to apply it everywhere across different scale. But in this case, it's sure that we cannot do kind of scaling across different scale. So that's pretty much about the work in this study. I have to acknowledge the students and technicians who take part in the field work at the very hot region of Alabama weather here, and also the funding agency. Thank you.
Thank you, Laura. My name is Christian Mercado, and as introduced, I am studying Western Larch. I'm with the University of Montana, and I'm funded by the Inland Northwest Growth and Yield Cooperative, and my advisor is David Fleck. So, Western Larch, or Larix occidentalis, is a deciduous conifer that grows almost exclusively within the Inland Northwestern region of North America. It is akin to Larix laricina or Eastern Larch. However, unlike its eastern counterpart, Western Larch holds considerable timber value. It generally grows tall and straight and can grow to large diameters with heights well over 100 feet. In each of these photos, larch is revealed by a golden yellow color. It naturally occurs across a range of forest species community compositions, sometimes as a minor component of a forest, like in the photo on the left here. and all the way to pure stands, like in the photo on the right. It is also very intolerant of shade, has fire resistant and resilient properties, and grows in subalpine environments, establishing well in mineral soil post-disturbance. So recent research has shown that forest species composition or species mixing can impact the growth of trees and stand yield, but until now, no such research has evaluated the impacts of species composition on the growth of western larch. Various models, like those in FBS, the diameter growth model there, have characterized how western larch grows. However, these models don't explicitly account for species mixture at this time. So the objectives of this research were, one, to identify whether community composition impacts the growth of western larch after accounting for other influential factors, and two, to determine how a species composition effect is best characterized. So here's a brief summary of the findings to consider as we kind of move forward. So first, after accounting for size, competition, and density, and site influences, there was a minor effect of composition on western larch growth. I used two different metrics to capture a community species composition effect. One was a relative abundance weighted by species identity, and the other was a relative abundance weighted by shade tolerance. I'll describe those a bit more later on. But result-wise, both metrics used expressed a similar minor impact on western larch growth. And as mixture decreased, the effect that it had on growth also decreased. So in other words, the growth of larch was impacted more when it was growing in more diverse communities. So with these things in mind, I will show you how I got to those findings. So using a long-term data set, which consists of repeat measurements across 18 forest stands in northwestern Montana, a generalized additive mixed model was developed to estimate the growth of western larch. For these data, trees were tagged and measured about 40 years ago, and subsequent remeasurements on the same trees and new trees were taken at varying increments of time since then. The map here on the left shows the rough locations of study areas used, where each dot represents a stand. Site conditions like slope, aspect, and elevation were variable across stands in the data. And the figure on the right is a histogram of western larch diameter at breast height, or DBH, where observations are color-coded by tree crown class. So as you can see here, tree size varied in the data set in DBH between 0 and 60 centimeters at the high end, and most observations were of codominant trees, as shown in green here, and the least amount of observations were of overtop trees, shown in very small purple bins, with a handful of observations of dominant and intermediate trees, shown by red and blue respectively. So since western larch is intolerant of shade and considered a pioneer species, it isn't too surprising that it holds a relatively dominant position in communities that it grows in. So in total, the model that was developed, it was informed by around 6,800 growth increments, which were recorded on about 2,400 individual larch trees. So no shortage of data. And from here, I'll show you some of the resulting model fitted relationships. So a little bit of explanation before I dive into these things. The model selection process used here involved accounting for variation by selecting variables based on the following groups: tree size, tree and stand competition and density, and site conditions prior to evaluating the effects of species composition. So variables were initially considered based on their use in other empirical growth models, as well as their availability in the data set. So this and each subsequent figure that I'll show displays a relationship where all other variables are held constant. And the further from the horizontal dashed line, the greater the effect the predictor variable has on western larch growth. So positive being being above the dashed line and negative being below the dashed line. So additionally, the y-axis on these figures shows the partial effect that the predictor has on the response. This means that for a given value of x, the estimated growth of larch will vary by the effect displayed on the y-axis. So now let's look at the impacts of some variables. Here on this slide, we see a figure of the partial effect on growth varying by tree size. which in the model was represented by DBH. The shape of this relationship is similar to the results of other growth models and shouldn't be too unfamiliar. And DBH on its own showed the largest influence on growth compared to all other individual variables in any group of variables. So it will appear on each of the subsequent slides to sort of give you some perspective side by side. So the table here at the bottom shows root mean squared error, or RMSE, in square centimeters per year in growth, where values closer to 0 represent a higher degree of model accuracy. And then at the far right is explained deviance, which essentially represents how well the model fits the data. So larger values of explained deviance indicate better model fit. So we see here that with DBH alone, the model is not particularly accurate and doesn't fit particularly well. But like I said earlier, DBH on its own did do pretty well comparatively. So moving forward, in the competition and density group of variables, crown competition factor, basal area larger than the subject, and crown ratio were selected in the final model. Crown competition factor's effect is shown by the figure on the right here, again with diameter on the left just for perspective. So back to crown competition factor, lower values here show a positive effect on tree growth, and higher values show a decreasing impact on growth. The degree of its effect is a bit smaller than that of DBH, so that's just an observation. Competition and density variables together improve the model accuracy and fit, as seen in the table below. We won't get too into those numbers yet. So slope and aspect together accounted for site conditions in the final model. The slope effect curve is shown here on the right and clearly has an overall smaller impact on tree growth than what we've seen thus far. Notice how the effect is somewhat variable across the range of slope. This is likely due to the clustering in the data set, where data are grouped together within stands and plots. So various trees can share values of slope across the data set and can pull that curve up or down, sort of depending on what the resulting growth rate is. However, only 2 site variables were included in the model and thus were meant to account for all the effects of site on tree growth. So some amount of visual noise in the fitted relationship pertaining to site is to be expected here. And again, these also improved RMSE and deviance explained. So for the sake of continuity, the improvements of RMSE and deviance explained by adding a tree level random effect are included in the table below. This represents the base model with which species composition terms were considered. So now I'll show some of the species composition results. So the curve on the right shows a larch fraction variable. That's larch fraction in quotes for those who don't see me, which represents the community level proportion of basal area taken up by western larch. So smaller values here indicate that a larch is surrounded by trees of other species, whereas larger values characterize a community with more western larch. Here we see a relatively small effect overall. This fitted relationship appears relatively stable, and we see an increase in western larch growth when larch is mixed with other species. And as a community becomes more homogeneous, we see less effect or slightly negative effect on growth, given that other variables remain constant. However, when this variable was added to the model, the increase in model accuracy, as shown in the table below, was very modest, and likewise, the increase in explained deviance with the term was somewhat marginal. So let's move on to the other variable that I used. So in this other metric, simply titled shade intolerance here, instead of weighting abundance by species identity, we weighted abundance by, oh no, something is wrong. Does everything look normal to you guys?
What are you trying to show? I can see here DBH, shade intolerance, and then I see the table with full model, larch, and shade.
Cool, yeah, sorry, I just had a weird little hiccup. Sorry, just let me get back on track here. Okay, so yeah, in this other metric, again, titled shade intolerance, instead of weighting abundance by species identity, we weight abundance by value of species shade intolerance scaled between 0 and 1. In this case, higher values indicate that a community is comprised more of shade intolerant species like western larch or lodgepole pine, for example, and lower values on the x-axis indicate a more shade tolerant community composed more of Douglas fir, true fir, or spruce, for instance. With this metric, species identity is not quite as important because shade tolerance is meant to capture how trees interact with light, and thus describes the mixed species competitive dynamics in a community. So similar to the larch fraction variable, we see an overall decreasing effect of shade intolerance on growth as a community becomes more homogeneous. When larch is mixed with more shade tolerant species, there appears to be a positive effect on its growth, again, at the lower end of that x-axis. And again, however, the increases in model accuracy and fit were very small here, so its relative impact on the overall relationship is small, but not unimportant. So kind of back to those conclusions that I showed before, species composition impacted growth where mixing was associated with more growth in western larch, but after accounting for other factors known to influence growth, the impact of community composition was relatively small. And then so kind of bringing this out to broader context, why is this all relevant? If a species mixing effect on growth is prevalent across species and communities, it can better inform models, and in turn, prediction and management can be better informed moving forward. Since modern management across the Intermountain West involves considering different values simultaneously, then better characterizing ecosystem dynamics in mixed species forests is sort of critical to making informed decisions down the line. And since western larch only grows across a relatively small area of the West, understanding how it interacts with other species can inform planting regimes, assisted migration efforts, as well as overall conservation-based management in a time where climate is so uncertain. And with that, I just want to thank you for the time and the opportunity for me to present my work to you. And I'll gladly take a question now. Oh, I forgot to mention this is also part of my master's thesis work. I don't know if I said that.
Like she said, my name is Austin Yantes. I'm a PhD student and I'm working on an oak savanna restoration project, and I'm really excited to share my dissertation research with you all today. Temperate oak savannas are beautiful park-like ecosystems that support an immense diversity of plant species and provide habitat for some bird, bat, and insect species that are rare or in decline. Savannas used to cover large swaths of North America, but unfortunately, due to agriculture and urban expansion, oak savannas have nearly disappeared. In the Midwestern USA, it's estimated that only about 0.02% of oak savanna acres still persist today. Any remaining savannas have really suffered from the removal of fire and large grazers from the landscape. And this is because fire and grazing function to suppress shrubs and saplings, and that maintains the savanna's characteristic open structure. So when you don't have those disturbances, remnant oak savannas often transform into woodlands that are dense and kind of shrubby. Due to their great habitat loss, imperiled status, and their high ecological value, there's been this really big push to restore oak savannas. So restoring remnant savannas involves reintroducing those fire and grazing disturbances. But our challenge is figuring out how we can recreate these dynamic, interactive disturbances that occurred historically using some kind of contemporary analogs, some that are better suited to smaller scale, the fragmented landscapes that we have today. In other words, we can't just have herds of millions of bison roaming through the suburbs. So we need other solutions. And that is the focus of our current work. So our study takes place at Sherburne National Wildlife Refuge in central Minnesota, USA. Oak savanna restoration here has been ongoing since the 1980s, primarily using repeated prescribed burns and then mechanical tree thinning, so just tree removal. The restoration goals that the refuge managers have set include 10 to 50% canopy cover of mostly Quercus macrocarpa, which is bur oak, and then 5 to 35% shrub cover, and then over 50% grass and forb cover. So we really want to see an herbaceous dominated understory. Our first aim was to look at how savannas respond to a gradient of different restoration efforts. So we ended up surveying areas that had 3 different restoration histories. We identified some areas that had been unmanaged since the establishment of the refuge. And then there were some areas that had been just thinned, so just had trees removed. And then lastly, there were areas that had been thinned and repeatedly burned throughout history. What we expected was that as you add in each layer of restoration action, the vegetation community would be pushed more and more and more towards those savanna goals that I just outlined. We identified 2 14-hectare survey areas to represent each one of those 3 restoration levels, and we surveyed 245 plots total. At each one of those plots, we conducted a comprehensive vegetation survey. So we were looking at the tree canopy, the shrub and sapling layer, and then the herbaceous community. Interestingly, what we found was that these different levels of restoration produce significantly different vegetation communities, which we can visualize with these 2 NMDS plots. So on the left there, we have the herbaceous community. The control and thin areas are in red and green, and those were really defined by some of the more shady, moister woodland species like lopseed and hog peanut, while the thinned and burned areas in blue had more of those sun-loving, drier species, aster, bedstraw, sunflowers. So again, moving from more woodland type to more opening species. And then on the right, we have the woody community. As we're moving from the unmanaged controls in red to the thinned and burned areas in blue, we can see this really cool shift from tree sapling species like red maples and oaks to shrub species like hazelnut and New Jersey tea. Putting those results back into the context of the refuge's restoration goals that I outlined earlier, we've got a figure here. On the left is an illustration of what's going on, and then on the right, we've got the numbers. So tree canopy cover is decreasing with each added restoration level. We're going from about 75% with the unmanaged areas all the way down to 28% in the thinned and burned areas. But herbaceous cover is kind of stuck. It's staying consistent around 30 to 35% and not increasing to that desired 50%. And then you can also see, looking at that lowest bar chart, that thinning and burning is really failing to control that shrub mid-story. Even after decades of restoration work, it's still way above the cover goal. And in fact, as we're adding these extra restoration efforts, shrub cover is actually increasing substantially, which is the exact opposite of what we wanted to see. So these findings are what really highlighted to us the need to find some kind of new restoration strategy that could be used to combat the shrubs and really push that understory to the herbaceous dominated community that's characteristic of savannas. So we set out to explore if grazing was maybe the missing piece in the historic disturbance regime puzzle. Specifically, we wanted to evaluate if targeted cattle grazing could be used to improve our restoration outcomes. And just so we're on the same page, targeted grazing is a type of really highly managed grazing that involves applying livestock at a determined season, duration, and intensity to accomplish a defined vegetation goal. So in this case, our goal is reducing shrub density. So another way to think about it is we're adding in this extra layer of effort, the cattle, on top of areas that have already been thinned and burned throughout history by the refuge. Again, just to try to shift that community towards our desired savanna goals. So we used short duration grazing, but at a really high grazing intensity to specifically target the shrub layer. We established 9 1/3 of a hectare paddocks and rotated the cattle through, spending only about 3 to 6 hours per paddock. So that's where that short duration comes in, just a couple hours. In 2020, we had a herd of 100 cattle, so we grazed them in these paddocks twice over the summer. And in 2021, we had 375 cows. So we only had to graze them once because the herd was so much bigger. We were able to get our impact by just passing through once. So maybe as you can start to imagine, 375 cows in a 1/3 of a hectare area is really where that high intensity component comes in. So this is what it looks like. Here's one of our grazing paddocks on the left. This is right before it was grazed. You can get an idea kind of what the shrub density looked like. And then on the right there is after only about 3 hours of cattle impact. So we're having a really high impact in a really short amount of time. Here's another one of our grazing paddocks. Again, on the left, you can see the shrub thicket and our cattle herd. And on the right is what it looked like after only 6 hours of grazing. So very high intensity, short duration. Each year, I surveyed these paddocks immediately before grazing and then immediately after. I looked at the shrub layer. And what we found is that targeted grazing has been remarkably successful in just 2 years. And really in just a few hours total, right? We've reduced shrub density by nearly 50%. I will note that we do need to ensure that we're also achieving our goals for the herbaceous layer. And as you can maybe imagine, it was just too sparse to really survey after last year's grazing event. So I'm returning in August of this year to assess after another full year of rest and recovery, just to make sure we are on track to achieve those herbaceous cover and diversity goals. I think that there are really 3 main takeaways from this project. First, we can layer contemporary analogs of historic disturbances to really improve our oak savanna restoration outcomes. We've seen that these strategies are more effective used in tandem than when they're used separately. Secondly, we've shown that targeted cattle grazing is a viable and powerful restoration tool, and it can be used to reduce shrub encroachment. And then lastly, and maybe most importantly, this project is an example of an innovative way to manage landscapes that integrates agricultural production with ecosystem health. And I just think that's really exciting. So with that, I just want to acknowledge all of our project partners, our funding through the Minnesota Environment and Natural Resources Trust Fund, and thank you to you all for listening. I'm happy to take a question.